After looking at Walter Lewin, we should have a good idea of what is actually going to be different about rolling objects. The name we have for this is the moment of inertia. We call it rotational inertia as well. But what's really going to be the impact here is not just the mass of the object, but the shape of the object. We can see if we put two objects that have the same shape, the same general shape, so two solid cylinders, we could adjust their radius, we could adjust their mass, and they're going to fall at the same rate. What's really going to change things is this coefficient right here. So if I have a solid cylinder versus a hoop, notice this coefficient would really be 1. If I have a sphere, the coefficient would be 2 over 5. Now, how is that really going to affect things? Well, to think about that, let's draw a ramp. Let's give this ramp a height. Let's say it's got a height of 10 meters, just for a nice even value. And then we're going to put 3 shapes at the top of this ramp. And I'm going to stack them on top of each other, but really they're supposed to be at the same level. So I've got a hoop, so we'll say green is the hoop. We'll do a sphere, so the orange will be the sphere. And then we'll do a solid cylinder. The solid cylinder will be that black color. So each of these is going to roll down. It's going to roll down the same path. It's going to go from this point down to this point right here. As each one falls, we're going to have a conversion of gravitational potential energy becoming kinetic energy, which we would represent with a K. And then the other part of it is going to become rotational kinetic energy. So let's designate that with this. Let's say K sub R. Now, how do you think rotational energy is going to be different from regular kinetic energy? Well, kinetic energy was this 1/2 mv squared. Rotational energy is going to have the rotational version of mass, which is moment of inertia. We represent that with a capital I. And then instead of a v, it's going to have the rotational version of velocity, which is angular velocity. That'll be squared. And then we'll still have that 1/2 qualifier there. And so when we have each of these objects rolling down, it has 1/2 mv squared plus 1/2 I omega squared. That'll be its final energy. Some of its energy is going to go into straight linear motion, but some of that energy is going to go into rotational motion. And so let's look at each one of these shapes. So I'm going to set up first the hoop. Now, instead of putting in I, I'm going to put in the equation for I. So for this hoop, the equation for I is mr squared. So I'm going to write in mr squared. And then instead of putting in the omega, I'm going to put in the way to convert omega to a linear velocity. If we remember, v equals omega r. And so if I rearrange that, I have v over r equals omega. And because omega is squared, what I get here is v squared over r squared. Well, now my radiuses cancel out. I have a common term in mass, m here, and m here, so I can divide each term by mass and lose it. And I will be left with if I simplify this one more step, I get GH being equal, and I'm going to put this all in green. This is my hoop. 1/2 v squared plus 1/2 v squared is v squared. Now let's try this for another shape. Let's see how things shake out for the solid sphere. So here's my general equation again, and then I'm going to substitute in my solid sphere's moment of inertia as well as the linear version of angular velocity. Once again, my r squareds cancel out. I can divide each term by mass and lose that. Notice I had 1/2 times 2/5. And so when I bring these two together, I'm not going to have v squared like I did over here. I'm going to have gh being equal to 7/10 v squared. Those are clearly two different values. Now let's do our last one. Our last one was the solid cylinder. Let's do that. Let's just do that to the right. Just like before, our r squareds cancel out. That should explain why the radius of these cylinders or spheres or whatever don't matter, because the r values cancel out. And once again, I can divide mass out of every term. That should explain why the mass didn't matter. But what I can't divide out is this 1/2 times 1/2. And so I still end up with gh equals 1/2 v squared plus 1/2 times 1/2 would be 1/4. 1/4 v squared. And so my final velocity of a solid cylinder would be equal to 3/4 v squared. So each of these shapes, even though they start at the same height, even though they might have the same mass, even though the masses don't matter at all, we're going to get different final velocities because of that multiplier. So let's go ahead and put numbers in here just to see how different these actually are. G is 9.8. My height was 10, so I get 98. So in each one of these, I'm going to have 98 for my GH. And in my first one, it's just equal to v squared, so I can just take the square root of 98. And I get 9.9 equals v. That's my velocity for a hoop. If I look at the solid sphere, well, that's going to be 7/10 v squared. So I'm going to multiply both sides by 10/7. And I end up with 140 equals v squared. And if I take the square root of both sides, I'll end up with 11.8 equals v. And now for my solid cylinder. For this one, I've still got 3/4 v squared, so I'm going to multiply both sides by 4/3. And I have 130.7 being equal to v squared. If I take the square root of that, I get 11.4 equals v. And so I can see if I raced these three objects, I would end up with my solid sphere in first, solid cylinder in second, and my hoop in third.